right, welcome to Lecture 10 from Introduction to Meteorology on thunderstorms and severe weather. The picture here from the book, a very typical supercell thunderstorm, very likely producing damaging winds, small hail, possibly even large hail, or maybe even a tornado. Very typical, what we refer to as a low precipitation supercell thunderstorm. So let's talk about thunderstorms and what is a thunderstorm and what's the difference between just normal rain and a thunderstorm. So any cloud producing precipitation, and it can be snow as well, but typically we're talking liquid precipitation. Any cloud producing precipitation that within the cloud or emanating from the cloud there is lightning, and if there's lightning then there will be thunder, that is a thunderstorm. And a thunderstorm can be made up of one single cumulus cloud, or it can be a cluster of many cumulus clouds, a multi-cell thunderstorms. Thunderstorms are convective, meaning there is an updraft and there is a downdraft. The updraft feeding hot, maybe more moist air into the storm, and the downdraft, where the rain is, bringing cool and dry air down. So thunderstorms are convective storms that form in rising air, often in conditionally unstable environments. Those environments that you have stability in the low levels, where you have to force a particle to rise, but once it gets to a point where it's reached its saturation and condensation is occurring, the release of heat from condensation, the release of latent heat, causes the particle to continue to rise all on its own. It reaches the the level of free convection. Then we have a convective thunderstorm. So what are the mechanisms to initially get that particle to rise in that stable environment? Because again, conditionally unstable means stable at the low levels and unstable aloft. The mechanisms are very similar to the typical mechanisms to get air to rise. Turbulent eddies, meaning winds that swirl around objects, can create turbulent eddies that can force air to rise. We see that with some types of land-based systems that develop, like water spouts and gustnadoes. Unequal heating of the Earth's surface. It can be as much as a hot area of asphalt, large area of asphalt, creating an updraft, or maybe the urban heat island effect of an entire city. Some cases, if we have a lot of cloud cover in the morning, but in another area it's full sunshine, where the cloud cover holds temperatures down, air will sink there, and where there was no cloud cover and the sun heated the land up, air will rise there, and that differential heating, that unequal heating, will create lift. We have the effect of lift up over terrain, or orographic lift. We have convergence along boundaries, whether they're cold fronts, warm fronts, or maybe even sea breeze fronts. We have upper level support. That upper level support can be divergence aloft, wind spreading apart aloft, or sometimes it's just cold air coming in aloft. Warm, moist air rising over frontal surfaces, and then also moving up over mountains and terrain, as we said.
Generally, there are two types of thunderstorms: a single cell or a single cumulus cloud, known as an ordinary cell thunderstorm, and then there's storms that comprise multiple cells or multiple cumulus clouds, and those are multi-cell thunderstorms. So an ordinary cell thunderstorm, sometimes called an air mass thunderstorm, because they form in those warm, moist air masses that are conditionally unstable. Not necessarily the ordinary cell thunderstorm, not necessarily associated with fronts or any type of severe weather. Many of the thunderstorms that pop up during our warm season over the Central Peninsula, or would be those ordinary cell thunderstorms, typically short-lived with a single cumulonimbus cloud, and rarely do they become severe. Now, the multi-cell complex or multi-cell thunderstorm, most frequently we see those. They contain a number of cells at different stages of development, and they form in those regions of moderate to strong vertical wind shear. So an ordinary cell thunderstorm, you're not going to have the wind shear. Once you get wind shear, winds changing with speed or height through the vertical profile of the atmosphere, that's when you're going to start to see multi-cell thunderstorms, and they are made up of clusters of cumulonimbus clouds, and they can last much longer than air mass storms, and oftentimes they do become severe. If the storm is able to become strong enough, a powerful enough updraft, any storm, whether it be an ordinary cell or a multi-cell thunderstorm, can become a severe thunderstorm. A severe thunderstorm is simply, again, a human construct, something we've defined. The term severe thunderstorm refers to a thunderstorm producing hail that's at least a quarter size, the size of a quarter, the coin, so an inch in diameter or larger, or has wind gusts of 58 miles per hour or greater, and or is producing a tornado. So any one of those three would make it a severe thunderstorm. So this is just how we define the difference between what could be a strong thunderstorm in the afternoon and a severe thunderstorm. So it really is about record keeping and whether we issue warnings or not. Lightning can be deadly, obviously, but the National Weather Service does not use it to define a severe thunderstorm. If it did, every thunderstorm would be severe by definition. There are levels in which they issue excessive lightning warnings, 12 strikes per minute. And there's also excessive rainfall and deadly flash flooding, but also heavy rain is not a severe weather criteria. The distribution of thunderstorms across North America, pretty straightforward. You're going to look for that combination of warmth and moisture, putting the highest distribution of storms smack dab in the Florida Peninsula from central to South Florida, and much fewer out in the Intermountain region and the drier regions of the country. You'll notice the maxima there around Lake Okeechobee. As we talk about shallow boundaries initiating thunderstorms, our sea breeze boundaries are big on that. That's why we get a lot of storms in central Florida. But Okeechobee can also produce lake breeze boundaries. So the combination of lake breezes and sea breezes over South Florida really providing them with quite a bit more thunderstorm activity on an annual basis. The life cycle of an ordinary cell thunderstorm or an air mass thunderstorm, any of those multiple triggering mechanisms occurs. We get some unequal heating, we get some uplift over some terrain or a little micro gust or swirl or eddy. At any rate, we get some uplift going. Warm, moist air is forced to rise. It cools until it reaches its dew point, at which it's at 100% relative humidity and saturation. Further lifting creates condensation and cloud formation, condensation being a warming process, aiding the parcel into rising on its own. So it's now past the level of free convection, and the growth stage, as warm, humid parcel of air rises, it expands and cools, condensing into a cumulus cloud or a cluster of cumulus clouds. As dry air begins to be pulled into that cumulus cloud, that's when we move into the mature stage. That dry air is entrained and falls, and the downdraft begins. And with that downdraft comes the rain. When you have the downdraft and the updraft, it constitutes a cell because you have up and down motion in the storm. And gust fronts, those cold air that's spreading out from the surface, begins to choke off the inflow in the updraft. And then once the gust front completely cuts off the inflow and weakens the updraft, there's nothing but downdrafts dominating the storm, which is then mostly rain. Other storms may form along those gust fronts, but that whole cycle took us about 60 minutes to occur.
So this animation is what it looks like with the updraft eventually turning into the downdraft, where you have the rainfall and that downdraft bringing cold air down that cuts off the inflow, the fuel for the shower and the thunderstorm, and eventually the storm itself begins to dissipate and die out. That is an air mass thunderstorm, an ordinary cell thunderstorm.
And here is a nice photograph of an ordinary cell thunderstorm somewhere out over the plains, and you can see just one cumulus cloud with a massive growth vertically. We get that very distinctive amble top on the upper levels and a heavy rain down there at the surface, but it's not a multi-cell, it's not in a cluster. And this particular thunderstorm all by itself, it could become strong enough to reach severe levels, but most likely it will rain itself out within that 60-minute time frame. The second type of thunderstorm is our multi-cell thunderstorm. This is the most common type of thunderstorms. They develop in areas of strong, moderate really, to strong vertical wind shear. And again, wind shear is going to be a change in wind direction or speed with height. And so in the low levels of the atmosphere at the surface, our winds are blowing in one direction or at one speed. And as you go up in the atmosphere, those wind speeds increase. And in this illustration, our winds are coming from the left to the right. And what that does is that allows the updraft to be tilted. So the downdraft that occurs and the rainfall happens away from the updraft. And even though gust fronts spread out, they do not necessarily spread out far enough because the storm is moving along and the updraft is tilted that it can cut off the inflow. So a UDI under that storm represents the updraft in this particular storm and the downdraft where the rain is. And again, you can see little fronts moving out at the surface, and that front may help to initiate new storms, but it's not going to necessarily cut off the updraft. So our multi-cell storm the mature cell right there in the middle, the dissipating cell, and then developing cells and new towers along the backside of it where we have the updraft and where the updraft has not been cut off. And that's how you get your multi-cell thunderstorm. And a nice view of multi-cell thunderstorms. In this situation, our storms are actually moving along in the opposite direction where we have the cell in the cumulus stage to the far right. So that's the growth stage. The mature stage, again, right there in the center, and the dissipating stage is to the left. So the storms are moving along from right to left, and the inflow, the updraft, is occurring on the right side of it. So that updraft's not being cut off, and new cells develop. And this is what we typically see in Central Florida when we get big clusters of thunderstorms occurring, is this type of multi-cell storm development. This is a little closer look at the concept of shear. On the upper right illustration, not only do we have directional shear, but we also have speed shear, where our surface winds are from the southeast, our low to mid-level winds are from the southwest, and that blue little net structure with the blue line at the surface is indicating that those mid-level winds are going to move into the storm and then be pushed down to the surface and spread out as gust fronts. And then those upper-level winds with a little jet streak right there in the middle providing upper-level support. So we have directional shear and we have speed shear. So air mass thunderstorms, they develop in low shear environments. Nothing tilts them. They just go straight up and then rain themselves out straight down. Shear is that change in wind speed or direction, or both, with height. When there's an unstable environment or a conditionally unstable environment, warm, moist air, with wind shear, precipitation in the downdraft can occur downwind of the updraft, and therefore you do not choke off the storm's inflow, and that allows for much longer lasting multi-cell storms. And oftentimes these storms, because those updrafts are perpetuated and they continue to have inflow from the surface, those thunderstorms become strong enough updrafts that you actually get severe thunderstorms. And the illustration on the bottom right, again, we can see the winds from the southeast are fairly weak, and you start getting into those mid-level winds. They're intensifying, and those upper-level winds are much stronger. Upper-level winds tilting that updraft in the vertical, so the downdraft and the rainfall is well out ahead of the updraft and the surface heating, and as that storm moves along, it's going to continue to have that updraft coming in from the southeast, that is, and that's going to continue to feed that storm, and you'll get multiple cells growing along this particular complex. Here is an overall view of a multi-cell thunderstorm, giving you all the different components and winds that are happening. If you look closely at the illustration, you have one mature thunderstorm with an anvil top and an overshooting top, and to its right you have new cells. So in this situation, the inflow is coming in from the right side of it, and the updraft is tilted, and the downdraft is off to the left, and it's not cutting off that updraft. Actually, it's even helping to create new cells out ahead of it. So the air motions and the different features associated with what would be an intense multi-cell storm. I say it's intense because it's got that overshooting top. That anvil top represents the top of the atmosphere, the tropopause. This updraft is strong enough that it punches through the tropopause into the stratosphere, creating that overshooting top. And then we have cold downdrafts. Again, you see the wind shear. At the surface, the winds are coming in from one direction. As you go up with height, they turn to the opposite direction, and they change dramatically. They increase the speed. And you can see that on the left, showing the wind, and that inflow at the mid-levels creates those very cold downdrafts. Those cold downdrafts produce gust fronts, so the leading edge of the cooler, drier air moving away from the storm. Shelf clouds, which are developed along gust fronts. Roll clouds also developed along gust fronts, and then outflow boundaries that move away from the storm, and then even downbursts associated with those colder, drier winds blowing in from the mid-levels and rushing to the surface. So a lot happening in a multi-cell thunderstorm. You can see where the new cell is forming. You can see the momentous that's hanging underneath that anvil top. Momentous, when that occurs and you see those types of clouds, you know you have a very strong storm. The warm, moist inflow and the downdraft area where the rain is. And in that downdraft area is where you're going to find the rain. The hail, likely. Sometimes that hail is ejected off because of those the updraft winds, but also that would be the area of the potential tornado. So we said that these multi-cell thunderstorms can produce a lot of different effects, a couple of them being gust fronts, shelf clouds, and roll clouds. So upper left, our illustration is just showing your basic downdraft. And when that downdraft is occurring, a couple of things are happening. The downward motion begins to pull colder, drier air, that entrainment of cool, dry air into the storm. Cooler, dry air is going to be heavier, so it will, once it gets going in that direction, moving down, will rush down to the surface. Also remember that there's always evaporation and condensation going in an unsaturated environment. And underneath the level of the cloud, it is unsaturated. So there's evaporation occurring. Evaporation is a cooling process. So you get this cool air and drier air that's more dense than the air around it, so it falls and rushes to the surface. It strikes the surface and spreads out. And the leading edge of that cooler, drier air is just like a cold front, little mesoscale cold front, and that's known as a gust front. Well, as that gust front rushes away from the core of the storm, it lifts the warm, moist air along and over it, and that's where we got these really ugly other types of clouds that form. The bottom left, that's going to be your typical shelf cloud, and those shelf clouds will develop underneath the base of thunderstorms as a whole separate thing and hang very, very low. And sometimes the entire shelf cloud will be in a slow rotation, indicating a rotating thunderstorm and the real potential for severe weather. And these roll clouds, a little bit different. These roll clouds, because of that downward rushing air, they get a little spin going, and these roll laterally. And you can see this long cloud that's rolling, kind of like a rolling pin, as they move away from the storm. Both the shelf cloud and the roll cloud, very, very ominous and very frightening, but always an indication of a thunderstorm that has reached that, almost reached that severe criteria, or possibly is, or will become severe. In addition to the gust fronts and the shelf clouds and the roll clouds that are created by the downward rushing, cool, more dense air, we also see outflow boundaries that move away from strong thunderstorms, strong multicellular thunderstorms. And this radar image, you can see a multicell storm with the far left red blob there, the one big storm, and then several others sort of trending off to the north and east. And where the cold air associated with the downdraft and cold air created by evaporational cooling underneath the storm itself rushes to the surface, spreads out as a gust front, it creates this outflow boundary that can be seen on radar. And you can see how it's moving away from this particular storm system. These outflow boundaries are one of those shallow surface boundaries that create convergence and help to initiate additional storms. And where outflow boundaries from one storm collide with other outflow boundaries from other storms, those are definitely points at which new thunderstorms form. So a radar image here of an outflow boundary, this cool, more dense air at the surface from the downdraft of the severe thunderstorm, or even just the strong thunderstorm, spreads outward and away from the storm center as it comes in contact with the surrounding warm, humid, less dense air, forming a density boundary. So there's literally a boundary of density differences, a shallow, almost like a front, and that's the blue line we see on the radar. This is known as the outflow boundary between the cool and the warm air, and along that outflow boundary, again, that's where new thunderstorms often form. Downbursts can be quite large, creating large outflow boundaries as seen in the radar image on the previous slide, or they can be quite localized. In this image on the upper left, cold air being entrained into the mid-levels of this thunderstorm moves downward with greater weight, higher density, and rushes to the surface, creating an impact on the ground in a very small area. And when we have these downbursts that extend 4 kilometers or less, they're classified as a microburst. And as you can see, these microbursts can produce winds of well in excess of 160 miles per hour, creating that little vortex ring we see in that image. Now, here's an actual image photograph taken where you can see the swirl of that microburst as it kicks up the dust underneath a thunderstorm. So these microbursts can really become quite strong and create some very, very strong straight line winds, damaging winds at the surface. But they're also a threat to aviation as well. This image illustrates how a downburst or a microburst, when it's less than 4 kilometers, can be a danger to a plane. A plane coming in from the right, it has a headwind at first, which provides it some lift, that wind blowing over the wings. And then it encounters the actual microburst, in which there's some downward pressure on the plane, literally pushing it down. And then as you move out of the microburst, instead of a headwind, now you get a tailwind, and the plane loses lift. And it can really cause a plane to radically increase in altitude and then very rapidly decrease in altitude. And if this occurs, a microburst like this occurs in and around an airport where planes may be taking off or landing, there's a real threat for airplane crashes with these microbursts. And so shear devices that measure shear in the winds around airports are now becoming more common, so they can warn pilots of exactly this type of situation. A squall line is our next type of multicellular thunderstorm. A squall line is a line of multicell thunderstorms that form along or ahead of a cold front. And oftentimes a squall line is right ahead of or right along the cold front, but more often than not, those squall lines actually advance well out ahead of the cold front, and then they're known as prefrontal squall lines. And sometimes they can be 100, even up to 300 miles out ahead of the cold front, where you get the main line of strong thunderstorms. And in terms of the length of these squall lines, as you can see from the radar image on the right-hand side, they can literally stretch for hundreds and hundreds of miles out ahead of that cold front. So how the squall line forms and why it progresses so far ahead of a cold front is still something that's being worked on, but the general theory, or the accepted theory, is that the prefrontal squall line forms as a gravity wave develops over the parent cold front and then moves well ahead of the front. And this is very similar to what happens when winds blow up and over a mountain, and it creates this up and down motion that continues downwind of the mountain. In this case, the wind blows over the cold front, it's lifted up, and as it sinks back down, this wave forms, and eventually at some point out in the very warm, humid air ahead of the cold front, enough of an upward motion is created that it creates that line of thunderstorms known as the squall line. Squall lines can be particularly dangerous, and mainly because of the very, very strong straight line winds that exist along the gust front that shoots out well ahead of the squall line itself. And so some squall lines, particularly at one end or the other, may have enough rotation in the storms that they produce tornadoes. But along the entire length of the squall line, you have this opportunity for very, very strong gust fronts and very powerful straight line winds, damaging straight line winds. So once again, you get this inflow in the mid-levels of the atmosphere. If you look at the illustration on top, in that 500 millibar level, just above, just below, somewhere, anywhere in that middle to upper levels of the atmosphere, those strong westerly winds flow into the backside of the storm. They are cold, they are dry, they become entrained in the downdraft, and because they're more dense, those winds rush to the ground, and when they strike the ground coming in at an angle, most of those winds rush out well ahead of the squall line itself. Now, two things happen. It forces the updraft to be tilted significantly, pulling very warm, moist air into the structure of the leading edge of the squall line and sort of enhancing the updraft. But that strong straight line wind that exits out ahead of the squall line as a gust front can be really quite dangerous. And so squall lines are known for heavy precipitation, a lot of lightning, but also for dangerous and damaging straight line winds. Squall lines create straight line winds that are damaging, enough so that we have a couple of names for those winds. The first thing we're looking at in both these radar images, the overall view is the bow echo. And the bow echo is achieved when a straight line, a squall line that is straight, receives so much of those very strong mid-level winds blowing into the backside of it that they literally blow the storms out ahead of the main squall line, and a bow forms, and that's known as a bow echo. What we know about the bow echo is those storms right there at the center, so the apex of the bow, those are going to be the most violent and the most powerful. And oftentimes, the winds associated with those bows, those straight line winds associated with the bows, will blow forward of the squall line itself for sometimes hundreds of miles, and creates what's called a derecho or derecho, but nonetheless, however you pronounce it, it's just an area of damaging straight line winds that can extend for great distances along and ahead of those squall lines. So bow echoes, when you see this on radar, you know that you're dealing with particularly strong part of the storm. Now, if you look at the upper left-hand image, you can see to the top of that bow echo, it shows a cyclonic rotation. Again, the bow is being pushed out. The cell back at the top of the bow is not moving as quickly, so a counterclockwise turning begins, and that particular storm may actually begin to rotate, and that's where you might most likely find the tornado. In addition, you can look at very, very long squall lines, as we saw in the slide two before this slide, very long straight squall lines. And if you get a number of these bows, you get, from a straight line, you get this radar image that shows one bow after the other, and sometimes those are called line echo wave patterns, indicating that there's a wave on your squall line, and that's a very good indication of a very powerful storm. And in each one of those kinks in that squall line is where you have the potential for tornadic activity. Yet another type of multicellular thunderstorm complex is a mesoscale convective complex. Mesoscale meaning it's bigger than the microscale, not quite as big as the synoptic scale. But what happens is if you have the favorable conditions, conditionally unstable environment, some shear coming into the west side of the system, lots and lots of warm, moist air, so typically in the southern to central plains, you get clusters of thunderstorms that begin to organize, in which the downdrafts and the updrafts of each thunderstorm sort of helps to enable the thunderstorm next to it to keep going, where the downdraft from one thunderstorm turns into the updraft of the next, and vice versa, and you get these clusters, and they're typically, actually, they look circular, as you can see here, and they are absolutely state-sized or even multi-state sized, and they can last for 6, 8, 10, 12, sometimes as much as 18 hours. They often form late in the afternoon as multicellular or clusters of multicellular storms sort of begin to organize together. And so typically we see these mesoscale convective complexes happening in the evening and then into the late overnight hours. And because they can exist at night when the atmosphere stabilizes. Again, the atmosphere stabilizes at night because the surface cools, but these are feeding on one another, so they maintain their instability by feeding on one another. And what's important about these MCCs is that they really do deliver most of the rainfall in the growing season in the Great Plains of the United States. And they're massive storms, and they come with a lot of lightning and gusty winds, but mostly it is just tremendous, heavy, and long-lasting rainfall. The next type of thunderstorm that we're going to talk about is one that you probably have heard about before, particularly in the media, known as the supercell thunderstorm. And this is actually not a multicellular storm. It's one storm, but what makes it special and different is, unlike the ordinary cell or the air mass thunderstorm, which grows up and then rains itself out, the supercell thunderstorm is one large cell that can develop into a steady state, meaning it becomes very, very long-lasting. And it becomes very, very long-lasting because one very, very powerful rotating updraft that typically is tilted exists in the storm. So there is a powerful surface inflow in this rotating updraft, and that rotating updraft is never cut off by the downdraft well out ahead of it. So you need a very strongly sheared environment. And if you look at the illustration on the left, we see surface winds from the south and mid-level winds from the north, and that very strong shear, so strong winds aloft, weak winds at the surface, north winds aloft, south winds at the surface, speed and directional shear, create literally these rolling tubes of air on the ground. Now, these rolling tubes of air, you can't see them. It's just where the air is generally going up and down in the cellular pattern, up and down a long tube. And it may not even be that strong, but it is a rolling tube of air. What happens is during the late afternoon, a thunderstorm may develop, and if it develops over top of that rolling tube of air, it can literally pull that tube into the upright, and as it stretches it all the way into the upper levels of the atmosphere, as you tighten up that circulation, the circulation dramatically increases, and you end up with this one violently rotating updraft in the thunderstorm. And again, typically it is tilted, and that violently rotating updraft is known as a mesocyclone. And it becomes a very significant entity all by itself within the thunderstorm. It's what can be seen on Doppler radar, and it's what helps to create tornadoes themselves. So strongly sheared environments, horizontal tubes of rotating air form on the ground. they can be tilted and stretched into the updraft of any given thunderstorm, whether it's part of a multi-cell complex or all by itself, and then that storm will begin to rotate. So these are very large, long-lasting thunderstorms with a single violently rotating updraft known as the Mesocyclone. So these massive steady-state storms are called supercell thunderstorms, and they can last 6 to 8 hours. This is what that mesocyclone looks like on your radar image. So upper right-hand corner, there's your radar image, and you can see Oklahoma City and different parts of Oklahoma and more there. And so what you're looking at is reflectivity. We're not looking at the storm relative velocity. We're actually looking at the amount of rain falling out of the storm. And you can see the big complex of the storm stretching from the northeast down to the southwest. And then right there at the southwest, it pinches off into a very, very well-defined hook. And that hook represents the rotating updraft. If you look at the illustration on the bottom, you can see that deep inflow coming in from the south and east. That's coming right off the Gulf of Mexico into the plains. And then as that winds, you can see they turn with height and they increase with height, helping to get that updraft spinning. And as those winds spin in that violently spinning updraft, that's the mesocyclone, they literally create an area where rain doesn't fall. It's such a strong updraft that rain doesn't fall. And so on radar, you get this region with very weak echoes. And so in the mesocyclone, you have this area of weak echoes, and it's bounded by rain being wrapped all the way around it. So they're called bounded weak echo regions, and they are very significant radar images that we look for. And that hook is known as the hook echo, and that's one thing that radar operators look for when they are looking at thunderstorms to see whether they'll possibly be tornadoing, because it takes that mesocyclone to get a full-blown tornado. And again, the illustration at the bottom gives you a nice sort of understanding of the mesocyclone and the supercell thunderstorm with a very powerful updraft, and then well out ahead of it the downdraft, but the downdraft not cutting off the inflow of the storm. As the storm moves along, it continues to get that real steady southeast that is, inflow that's very warm and very moist. So the mesocyclone again, our illustration in the bottom left shows you your rolling tube of air. It shows you your winds blowing from the southeast to the surface, bringing in warm, moist air in the inflow, the mid-level dry air being entrained into the storm, helping to create the downdrafts, and then the very powerful upper-level winds with the jet core embedded in it that's helping to aid in the divergence aloft and therefore the convergence at the surface of that very powerful updraft. And again, this is the area where you're going to have your bounded weak echo region or your hook echo. And you can see to the right, this illustration shows what's happening at all these different levels. At the surface, that thunderstorm is out ahead of a cold front, cold dry air coming in at the surface and more moist air coming in from the south and southeast out ahead of the low. In the low levels, that 850 to 700 millibar level, you have a south to southwest wind flow. At the very lowest levels, the low-level jet is a very warm, moist flow. But once you get up above about 700 millibars, it begins to entrain much, much drier air from the upper levels, 10,000 feet or above. And then at that 500 millibar level up to 300 millibars, you have the trough in the long wave of the atmosphere with that little short wave digging through it, and the jet streak moving through it in that trough at 500 millibars and 300 millibars, all helping to provide additional uplift off the surface, which allows our supercell thunderstorm to really have that strong upward vertical motion, creating that one violently rotating updraft. Here is a nice illustration of your sort of standard supercell thunderstorm, all the basic components in place. Your violently rotating updraft, that is the mesocyclone, which can be as much as 5 kilometers wide. You have the downdraft well out ahead of it, the forward flank downdraft, and where you have a very heavy rain, perhaps some hail. The gust front that is moving well out ahead of the thunderstorm itself, which is helping to provide additional thunderstorm development. You have the anvil top at the tropopause, which underneath it you're getting some virga, but you're also getting some mantis that develops as that rain falls out of those upper levels. The anvil top at the tropopause, the overshooting top up into the stratosphere, indicating just how powerful the storm is. We see surface inflow from the south and southwest, and then in the mid-levels into the upper levels, those winds become stronger, helping to tilt that updraft into the vertical. But here's a concept that we haven't discussed yet. That updraft is so powerful that winds literally don't blow through it. It becomes like just a spinning column in the atmosphere. So those powerful upper level winds that are coming in from the west and the northwest, they literally strike that updraft. And some of the winds are deflected around it, but some of those winds can't go through it, and they just go straight back down. So the forward flank downdraft is a function of rainfall, some cold, dry air being entrained into it, with the cold air rushing to the surface, and rainfall and hail. But that rear flank downdraft is a function of very powerful upper-level winds striking the mesocyclone and then rushing down. And even though this illustration doesn't show it, sometimes that rear flank downdraft begins to rotate itself. And in the space between the mesocyclone and the rear flank downdraft, a mid-level, so we're talking 500 millibar, 5,000 meters up, a mid-level vortex can begin to develop, and that rear flank downdraft literally pulls that vortex down the surface. And when that vortex exits the bottom of the cloud, you get a wall cloud and then eventually a funnel cloud, and when that funnel cloud touches the ground, then you have your full-fledged tornado. Here's a great photograph of a supercell thunderstorm that has formed in a very dry environment. So this would be a low precipitation supercell thunderstorm. The cloud base is very, very high. This is somewhere out in the plains. There's just not enough moisture, but all the other components are in place. And you can see the cloud base that represents the mesocyclone, which is likely turning, the shelf cloud underneath it, the mid and high clouds in the anvil top, and then of course the tornado and the dust whirl that exists all around that tornado. And one more illustration giving you more of a top-down view of that supercell thunderstorm, where you can see that anvil top and the winds aloft coming into the back of the mesocyclone, creating that rear flank downdraft. And in this illustration, some indication of that rear flank downdraft beginning itself to rotate. The forward downdraft with the showers, the lightning, and also the hail, the gust front exiting away from that forward flank downdraft, but also a gust front exiting away from the rear flank downdraft, and then that inflow, that warm, moist flow, gets fed into that mesocyclone in that tilted updraft. So very good illustration of your supercell thunderstorm. So we know that when we look at these storms with radar, we can see, one, the rain falling. The radar is listening for the reflection of the electromagnetic radiation to bounce back to the radar site. It literally bounces off the rain, and we can hear, and that's what I call it reflectivity, the actual amount of rainfall. But we've also talked about Doppler radar, where we can see which way the winds are moving and how fast they're moving. And so it's that Doppler radar that can see that 5 kilometer across mesocyclone, and they're not all that big, and some are actually bigger. But on one side of that mesocyclone, it can see the winds moving away, the Doppler, and on the other side, it can see the winds moving toward the radar site. And it's where we have those signatures on radar. We know we have a mesocyclone. We also have the addition of being able to see the hook echo on the reflectivity. And that is when we get what we call a tornado vortex signature, or the radar, algorithms of the radar recognize the spinning of the wind and the hook echo, and they generate a tornado vortex signature, which lets us know that this particular storm may be tornadoing. The rotating thunderstorm, or the mesocyclone, and how we see that on Doppler radar. Remember, the Doppler shift is the shift in the frequency of waves based on the motion of the emitter toward or away from the receiver. So the receiver is the radar site, and the emitter is going to be the EM, the electromagnetic radiation, bouncing off the raindrops. And so imagine that in the illustration with the person there, imagine that the ambulance, in this case, is the raindrop. And of course, what they're showing you is the sound being emitted from the ambulance as it approaches the listener. Those sound waves are scrunched together, and it's a higher frequency. And as it moves away from the listener, the sound waves are pulled apart, and it's a lower frequency. In the case of the raindrop, it's radiation bouncing off of the raindrop, going back toward the radar site, and that radiation coming back toward the radar site when the rain is moving toward the radar has a higher frequency, and where the rain is moving away from the radar, it has a lower frequency. And when we have the radar using the Doppler effect, listening to those frequencies and not looking at the reflectivity of the amount of rain, then that's called velocity. And we'll take a look at a couple of radar images comparing the reflectivity, the amount of rainfall, to the velocity. So we'll start this slide with a look at my blue illustration at the lower right-hand side. At the top, the three little raindrops, the green little raindrops, they are moving away. Okay, the winds are moving away from the radar site. At the bottom, the raindrops are moving toward the radar site. On both illustrations, the wavelength of the electromagnetic radiation leaving the radar is the same. It's that white wavelength that has the same wavelength, the same frequency. At the top, where the raindrops are moving away, the wavelength coming back is shifted to the red, it's longer, and the wavelength coming toward the radar site is shifted toward the blue, and so it's going to be shorter. And that's how the radar sees whether the wind's blowing toward or away from the radar site. So the top two illustrations, you can see on the left, that's straight reflectivity. That is the radar just listening to how much electromagnetic radiation is bounced back to the radar site. It's just listening. And it's painting where lots is bounced back, the deep reds and the purples, and where very little is bounced back, it's the light blues. The heaviest rain is in that red area. And you can see where the hook echo is wrapping around the mesocyclone. So if that same radar image is then switched to reflectivity, the radar will paint the winds moving away in these warmer colors, these reds, and the winds moving toward the radar site in these cooler colors, the greens and blues. And so if you look at that same location of where the hook is, you can see that we have very, very bright red moving away from the radar site on the top, and that very, very light green moving toward the radar site on the bottom. And what that's telling us is winds are moving away on the top and moving toward the radar site on the bottom. And that whole section of that storm is literally rotating. Now, if we look at the bottom picture, very, very similar, the reflectivity is showing us that hook echo where the heaviest rain is wrapping around the mesocyclone. And again, that area in there where there's not much rain, that is the bounded weak echo region. And then you look at that location just north of Moore, and you can see when we're looking at the storm relative velocity, we're looking at the velocity image, and you can see that from the radar site on the far right, just to the top, the red indicates that those winds are rushing away, and on the bottom, the green indicates the winds are moving toward the radar site, and that is where our rotating thunderstorm is. And again, that's how radar detects mesocyclones. Radar doesn't detect the tornado. They detect the mesocyclone. And if the mesocyclone is strong enough and through a deep enough layer of the atmosphere, the radar will then produce the tornado vortex signature, and that is where we get these Doppler indicated tornado warnings. We haven't quite seen the tornado, but we have a tornado vortex signature, and we think there probably is one developing in that region. One more set of pictures here. Again, this is Tuscaloosa, April 27th of 2011, and you can see the bottom right-hand side, the very pronounced hook echo where the rain is wrapping around the mesocyclone, and even that little purplish area where the line says debris. Using the dual pole Doppler radar, we can tell what type of precipitation is. We can see that's tornado debris in the air right there. And then when you look at the one on the left, you can see the reds where the winds are rushing away and the greens where the winds are rushing toward the radar site. And again, indicating that counterclockwise turning of the mesocyclone. And so if you were an Alabama weathercaster working on this afternoon in April, those would be the radar images that you'd see, and that is how you'd be warning people there could be a tornado on the ground at the university in Tuscaloosa, even if you didn't have a report yet that there was a tornado on the ground. Of course, in this situation, there was lots of reports of tornadoes, but that is a radar image that you'd be looking at. By definition, a tornado then is a violently rotating column of air in contact with the ground. And a funnel cloud is a tornado whose circulation has not quite reached the ground. So for it to be a tornado, it has to actually get down to the ground. So we do have a lot of funnel clouds that dip out from underneath clouds, stretch toward the ground, but don't quite have enough dynamics in place to make it to the ground. Those are tornado clouds. They can create dust swirls and some debris as well, but a tornado has to be in touch with the ground. And the life cycle of a tornado is the funnel stage, the mature stage, and then the decay stage. And the funnel stage is known as the dust swirl, short funnel from the cloud base and a whirling dust to the surface. That mature stage is, of course, its most intense when that funnel is nearly vertical. And then once you start to get those ropey types of tornadoes that you see, that is the rope cloud stage, and that is when the tornado is weakening. Tornado occurrences, no huge shock. By the way, the U.S. has more tornadoes than any other country. Most occur in the spring and early summer, and most in the late afternoon. And this is the average annual tornadoes per 10,000 square miles. And of course, Tornado Alley is going to stretch from the panhandle of Texas through Oklahoma, on up into Kansas, and then into Missouri, Iowa, and Illinois. We also have a nice maximum of tornadoes around the Gulf Coast, and of course here in central Florida. And as we can see from the number of tornadoes per month, most of them are going to happen in the spring and then on into the early part of the summer. In the spring is when the cold air that's already pushed south for the wintertime is just beginning to retreat. Warm air is just beginning to push north, and it's the combination of the very cold air from winter interacting with the warm air from spring that develops as very strong mid-latitude cyclones, and therefore more intensity to the thunderstorms. A quick peek at the Fujita scale, and then we'll move on to non-supercell tornadoes. It's actually the enhanced Fujita scale, changed about, 8-10 years ago maybe. All scales in weather, whether it's the Fujita scale for tornadoes or the Saffir-Simpson scale for hurricanes, the defining factor, we always think about wind speeds, but the real defining factor is how much damage they do. Because once we start looking at wind speeds above 120 to 130 miles per hour, even in some cases above 100 miles per hour, typically you don't have the type of instruments that can be in those winds and survive. And you certainly don't have the type of instruments that are going to survive a 200 mile per hour wind. So these different categories, these stronger categories, are mostly determined by the type of damage that is done when the tornado goes through. So here's your enhanced Fujita scale from F0 to F1, which is mostly what we see here in Florida, to the F2, 3, 4s, and of course the 5s that they see out in the Tornado Alley area of the Central Plains. And the Central Plains, again, where the cold air from the north and the warm air from the south most easily meet, and it's that combination of cold and warm and moist that gets those violent storms going, that creates the very powerful updrafts and the potential for tornadoes. Here is the Fujita scale and its impact on a given farm, and so we can also see the tornado in the background, give us an idea what it likely looked like. F0, you're going to have some branches down, maybe some shingles off of the roof, and it looks like there's a little bit of debris there, pink debris in the yard next to the driveway. You get that EF1, so now you're up above 100 miles per hour. The trees may be uprooted. There may be just a little bit more than shingle damage to your roof. You may even have some plywood pulled off the roof. Maybe a little bit of damage to the lighter building, the little garage there. You can see the car has been moved just a little bit. You get up to EF2, 111 to 113. Now we flip over cars. We demolish weak buildings such as garages and carports. The structure of the roof has now been pulled away. There's been some additional damage done to the house itself. EF3, you have significant damage to the house. EF4, complete damage to the house. And in EF5, the entire home is scraped off the foundation. All that is left is maybe a bathtub and some pipes sticking up out of the concrete foundation, which is why, by the way, if you're ever in the path of a tornado, that interior room, bathrooms, but if you really are in danger, path of a tornado, if you can get a mattress, or several mattresses, and get in the bathtub and cover yourself with the mattresses are going to protect you from falling debris. And if the bathtub is cemented into the floor, now I'm not talking about the upstairs bathroom, downstairs bathroom, if it's cemented into the floor like they so often are, that has the best chance of staying put in these powerful tornadoes. And again, you can see the tornadoes in the background and just how large those EF3, 4s, and 5s can be. Non-supercell tornadoes, meaning either a land spout, or I should say a water spout that develops without any thunderstorm at all, or a landspout or a gust tornado that develops with just a normal thunderstorm. Typically, at the surface, you have some pre-existing spin, some boundary that's creating some turning in the atmosphere, and then a thunderstorm develops and moves over that pre-existing spin and pulls that spin up into the atmosphere. So these landspouts are going to be where you get your dust devils and gust tornadoes. We had gust tornadoes during Charlie, where the winds swirling, the eddies being created by the powerful winds blowing through the neighborhoods created swirls, and then as the individual thunderstorms moved over those swirls, the updrafts of the thunderstorms pulled those swirls up, and you got what's known as a gust tornado, weak tornado, forming along a line of thunderstorms. Of course, the landspouts and the waterspouts, all surface-based. Remember, our tornado from the supercell, it came out of the middle levels of the atmosphere, so these landspouts and waterspouts are all surface-based. They tend to be weaker and much more short-lived.
Here in the Andes Mountains, you also have geography playing an important role in severe thunderstorm development. The two air masses collide. The warm, moist air from the Amazon basin collides with the cooler air from the South Pole. It mixes, and the warm air is pushed up by the mountains and forms some of the most severe thunderstorms on Earth.
Jim sets off to try and get underneath the center of a developing storm. The lightning is a byproduct of the extreme air movements within storm clouds. Inside the storm clouds, warm, moist air rises. As it gets higher, the temperature drops and the water particles freeze. Some become small ice crystals, others larger slushy ice. In the turbulent storm, the two different types of ice crash into each other and become electrically charged. A huge electric field begins to build up until it becomes so strong it reaches for the earth below. But higher in the atmosphere is a much more elusive, much more exotic form of lightning that even Jim has never seen. They're called sprites. This is a type of lightning that doesn't strike down towards the ground, but instead reaches upwards, sometimes as far as 75 kilometers high into the stratosphere. They're rarely seen because they happen so far above the Earth.
Moving on now to lightning, and of course lightning is what makes a thunderstorm a thunderstorm. Lightning is a discharge of electricity in or from a mature thunderstorm. Now, it has to be a mature thunderstorm because it has to have the height to get this charge separation, and it has to have the height for the charge separation to be able to occur. The charge separation occurs basically as ice becomes electrically charged, either positively or negatively, and sometimes water droplets, but it really takes the ice to do that. So one of the things needed for lightning is for there to be some ice. Now, mid-latitude storms, anything Florida or north, definitely going to have ice in it. But some of our storms in the tropics, they'll be a little rumbly, but they won't have significant lightning. And then oftentimes, tropical cyclones and the storms associated with that won't have a lot of lightning with them either, because essentially the storms are so warm, there's just not a lot of ice. So you have to have a mature thunderstorm, and that lightning occurs when there is an electrical charge separation, known as an electrical potential, that becomes strong enough that it can overcome the insulating properties of air. So insulation just means electricity can't or has a very difficult time passing through the insulating body. So we know that copper wires are wrapped in rubber. Rubber is the insulator. The bigger and stronger the wire, the thicker the insulation is going to be. Enough electricity. It can move through that rubber, but it's a great insulator. Wood is a great insulator. Enough electricity, it can also move through that. Electricity can move through water. It can move through the ground. It certainly can move through metal very easily because electrons move very easily. But air is a good insulator. And so it takes a lot of electrical charge to overcome the insulating properties of air. When there's enough electrical potential, difference between positive and negative, then there is a connection between the two, and there's a discharge, and that discharge is the lightning stroke. So the charge separation, or the electrification of clouds, occurs when larger negatively charged particles fall to the base of the cloud, and smaller positively charged particles are lifted to the top of the cloud by the updrafts. There is a net transfer of positive ions from warmer, heavier objects to the colder and lighter objects. So positive ions, by bumping into one another, by colliding with one another in the up and the down drafts as these objects move by each other, positive ions move from the heavier, warmer objects to the colder, lighter objects, and you get generally a positive charge at the top of the cloud and a negative charge at the bottom of the cloud. And for most lightning strikes, about 80%, the lightning discharge happens either within the cloud or between two clouds that are next to each other as this charge separation occurs. The cloud-to-ground lightning occurs when the negatively charged base of the cloud literally induces a positive charge in the objects below, meaning positively charged ions are literally pulled up to the top of the objects because of the negative charge of the base of the cloud. And then you can see in this illustration there's a charge separation between the base of the cloud and the object below. So the charge separation between the cloud base and objects in the ground develops as negatively charged cloud base induces a positive charge at the surface because, again, opposites attract. Here is an illustration of that electrification of clouds where the warmer, heavier hailstone gives up some of its positive ions as it connects with that smaller, colder ice crystal. And the smaller, colder ice crystal becomes positively charged and goes up, and the hailstone becomes negatively charged and falls to the surface. So ice, as I said, is generally required for the electrification of clouds. So the lightning stroke itself is a fairly complicated thing, and it's something we see very, very regularly, and it happens very, very quickly, and huge discharge of electricity and heat. What happens in cloud-to-ground lightning, which is about 20% of lightning, it begins when the charge separation between the Earth and the base of the cloud is great enough that it causes a channel of negatively charged electrons, known as a stepped leader, to move toward the ground. So A, you've got your step leader. You don't see this. It's a channel of negatively charged electrons reaching toward the ground. And the reason why lightning is forked and it looks so tortuous is because it doesn't know where it's going. It's just reaching out for that positive, and it sort of darts back and forth. As it approaches the ground, a similar positively charged channel begins to climb toward the step leader, and that's coming up from the object on the ground. When the two connect, the positive current rushes back up the step leader, and the luminous return stroke is what we see. So again, the charge potential is highest where it's positive, so the positive goes towards the negative, and that's what lights up the lightning channel, and that's what you see. So if you've ever heard lightning goes from the ground up, the positive ions go from the ground up, and that's what you see. Why you see it stretching down, it's kind of a trick of our eyes, but the step leader draws down, the return stroke illuminates, and it goes up. And the return stroke instantaneously heats the surrounding air to 30,000 degrees Celsius, about 54,000 degrees Fahrenheit, and that creates the shock wave that we hear as thunder.
So this animation is going to show us the development of a typical thunderstorm. Here is the updraft, and that updraft along with the downdraft of the rain allows for the electrical charge separation and the electrification of the cloud. Negative charge at the base of the cloud induces a positive charge on the objects below. A step leader reaches out toward those objects, and when the step leader gets close enough to those positive charges at the surface, and then the step leader connects and the return stroke occurs, and then the cloud kind of goes and dissipates its charge separation and continues to move on, and additional charge separations may form, which may allow for intra-cloud charges or lightning strokes, or maybe more cloud-to-ground lightning strokes.
A little bit more detailed. It also gives us an indication of why we get the flashing or the multiple lightning strikes, because the first return stroke helps to equalize the charge separation, but sometimes it requires several to totally dispel the charge separation. So read through this. Pretty good little illustration of how the lightning stroke occurs as well. Different types of lightning. You may have heard of forked lightning, ribbon, bead lightning, ball lightning, sheet lightning. By the way, ball lightning is oftentimes what they call St. Elmo's fire. Sheet lightning is basically intra-cloud lightning. And the concept of heat lightning is basically thunderstorms way off on the horizon that folks at one time saw often in the heat of summer. They saw the lightning, but they didn't hear the thunder, and they referred to that as heat lightning. So heat lightning is just any old form of lightning that somebody sees, but they actually can't hear. And again, different types of lightning. We have the cloud-to-ground lightning. We have the intra-cloud lightning, cloud-to-cloud lightning. And the last thing I wanted to point out to you is this lightning that reaches out from the side of the clouds or sometimes the top of the clouds. And because if they come from the top of the clouds, it's actually a positive strike coming down, that we are talking about what's known as bolts from the blue. And these are capable of traveling, in some cases, upwards of 30 miles away from the base of the thunderstorm. And this is the reason why, if you're at New Smyrna Beach and there's thunderstorms well inland and they're ugly and they're stormy and you think, well, the sky's blue over me, we're okay. Even in that situation, a bolt from the blue is not impossible, and lightning strikes can occur. And again, lightning strike heats the channel of air around it up to about 50,000 degrees Fahrenheit, about 5 times the heat of the surface of the sun. So certainly not something to play with. We will wrap up this lecture with just a quick peek at thunder. And then, of course, our next lecture, Lecture 11, is going to be looking at hurricanes, tropical cyclones, and so that will be an interesting one. Thunder is the booming sound wave caused by the explosive expansion of heat as lightning heats the column of air around it to more than 54,000 degrees Fahrenheit. It takes about 5 seconds for the sound of thunder to travel 1 mile from the lightning strike. If the sound waves from the lower part of the stroke reach an observer before the waves from the upper part of the stroke, then you start to get that rumble of thunder. And also it takes lightning being quite a distance away to get a rumble. The rumble also occurs because the sound wave may have ricocheted off of buildings or mountains or trees or even other clouds. And so when you're very, very close to a lightning strike, you tend to get a clap, very, very high-pitched clap and a bang. Whereas if you're very, very far away from thunder, it'll be much, much more rumbly and last much longer. In some cases, those sound waves strike the ground and bend upwards. So observers at a certain distance from thunderstorms sometimes can't even hear the thunderstorms. So again, this wraps up our lecture on thunderstorms. Next is going to be tropical cyclones, hurricanes, tropical storms, and tropical depressions.
So we will see you next time for Chapter 11, from Introduction to Meteorology, Tropical Cyclones.